Let's take another counter design problem. This time we are going to design a counter using JK flip-flops, and we are taking the same pattern as we have looked at for the T flip-flop counter. Again, the concept is the same. First, try to identify the number of flip-flops that you require. If you look at the pattern has 3 bits. Therefore, you require 3 JK flip-flops. The first step is construct the excitation table. So you have QC, QB, QA. Similarly, QC plus, that's the next state, QB plus, and QA plus. Now JK flip-flop has two inputs, the J input and the K input. So you require JC KC, JB KB, and JA KA. So let's come up with the truth table 0, 0, 0. So when it is 0, 0, 0, next state is don't care. So all of these will be don't care as well. When it is 0, 0, 1, next state is 1, 1, 0. When it is 0, 1, 0, next state is don't care. So your J and K inputs are don't care as well. When it is 0, 1, 1, next state is 1, 1, 1. When it is 1, 0, 0, next state is don't care. So these are don't cares as well. When it is 101, next state is 001. When it is 110, it's 011. And when it is 111, next state is 101. Now we need to find out the inputs JC, KC, JB, KB, and JAKA. To do this, first you write the truth table for a JK flip-flop. So in a JK flip-flop, you have J, K, Q, and Q plus. So you have 8 combinations. When J and K are 0, 0, that's the hold state. So Q plus is equals to Q, hold. When J is 0 and K is 1, that's the reset operation. Remember, your JK flip-flop is similar to your SR flip-flop, with the exception that an SR flip-flop is not designed to be correct when both the inputs are 1 and 1, but a JK flip-flop is designed in such a way that even for 1 and 1 it is valid. When J is 1 and K is 0, that's the set operation. Oh, this is the reset, so it's going to be 0, 0. And this is set, so it will be 1, 1. And when J is 1 and K is 1, that's the toggle operation. So in toggle operation, when Q is 0, Q plus is 1. And when Q is 1, Q plus is 0. Now using this table, let's construct another version of this table where we have Q, Q plus, J, K. The combinations are 0, 0, 0, 1, 1, 0, and 1, 1. So if Q is 0 in the current state and Q plus is 0 in the next state, what are the values of J and K? Same for the other combinations. So when Q is 0 and Q plus is also 0, which is this combination and this combination, J is definitely 0 because J is 0 here and J is 0 here. It doesn't really matter what the value of K is, so we put a don't care. Similarly, when Q is 0 and Q plus is 1, which is this combination here and this combination, J is 1 and K is 0 in one case and 1 in the other case, so it doesn't really matter. Now when Q is 1 and Q plus is 0, which is this combination here and this combination, your J is 0 in one case and 1 in the other case, so that's don't care, and K is basically 1 and 1. Sorry, 1 and 1. So it's 1. Similarly, when Q is 1 and Q plus is 1, which is this combination and this combination, J is 0 and 1, so it's don't care, and K has to be a 0, which is this and this. So using this table, we are going to fill up this table here. So when QC is 0 and QC plus is a 1, which is this combination, you have 1x. Again, when QB is 0 and QB plus is 1, you have 1x. When QA is 1 and QA plus is 0, which is this, it's x1. Similarly, QC is 0 and QC plus is a 1, so you have 1x. You have QB1 and QB plus is 1, 1, so you have x0. Again, you have 1, 1, so that's x0. 1, 0 would be x1. 0, 0 would be 0x. 1, 1 would be x0. Similarly, 1, 0 would be x1. 1, 1 would be x0. 0, 1 would be 1x. 1, 1 would be x0. 1, 0 would be x1. And 1, 1 would be x0. So now we have completed the excitation table. Now find out the equations for JC, KC, JB, KB, JA, KA using K-maps. So once you get that, you will have 6 equations: JC, KC, JB, KB, JA, and KA. And then you can construct the circuit diagram. So this is how you can design counters using JK flip-flops. It's very similar to your D flip-flop and T flip-flop. Once you have the excitation table, come up with the K-maps and find equations for JC, KC, JB, KB, and JA, KA.